Welcome to Lab 3, Circuits. In this lab, we predicted the behavior of circuits with resistors in series and parallel, used multimeters to record the experimental values of current and potential difference, and compared experimental results to theoretical. Current in the two-resistor circuit was measured to be 0.0192 amps. The calculated values and experimental values for current and potential do not agree. And it was discovered that the larger the resistance of a resistor in an RC circuit, the longer it takes for a capacitor to charge and discharge. We have a few principles, including the node rule, which is a conservation of charge statement. Pretty much just says that the amount of current entering a junction is equal to that leaving the junction. And our loop rule is a conservation of energy statement. Due to path independence, the potential difference of a round trip through a static electric field is 0. The potential difference across an ohmic resistor is found to be current times resistance, and we have two separate equations for determining the total resistance in a circuit depending on whether or not they're in series or parallel. And we have capacitance is a physical property of a material and a measure of how much charge a capacitor can store per unit of potential difference. We have a system of the device measuring the current or potential difference and the surroundings to be the circuit itself. In our initial circuit, we had 2 batteries, 2 resistors, and 2 ammeters. The predicted current was calculated to be 0.0204 amps, and the actual current was measured to be 0.01925 amps, with, of course, the reversed ammeter reading to be the negative of the actual. In our open circuit, we had the same setup as the initial, except one ammeter was transformed into a voltmeter, and we predicted that the potential would be 3 volts and the current would be 0 volts. A voltmeter has significantly large internal resistance, which would prevent the flow of current. So this would essentially be modeling an open circuit. And our experimental values were found to be 3 and 0, and so the experimental and predicted values agree. For the potential difference around the circuit, we had the same circuit as previously, but this time closed with a wire. The potential difference across each circuit element was measured to be negative 0.8, negative 1.9, and positive 2.9 volts. The sum of all potential differences in the loop should be 0. However, experimentally, they were found to be a non-zero. And this is due to errors in measurement, incorrect connection of circuit elements, and internal resistance of batteries. For the ammeter in parallel, the previous circuit was reconstructed with an ammeter placed in parallel to the 100 ohm resistor. The current measured across the ammeter remained the same. Theoretically, the current measured across the ammeter should have increased because the current was split into junctions. Only some of the current passed through the resistor and the rest did not, and so the total current should have increased after the junctions met. So there could have been errors in measurement and incorrect connection of circuit elements. The experimental values of resistance are calculated using Ohm's law, and it was found to be 42 ohms, 99 ohms, 0 ohms, and 0 ohms. An RC circuit was made with 2 batteries, a 1 farad capacitor, and 1 light bulb that was 10 ohms. After the battery was connected, the bulb gradually dimmed. As the capacitor charged, the current across the circuit decreased. The battery was then disconnected from the circuit, and the capacitor was directly connected to the bulb. The brightness of the 10 ohm bulb gradually dimmed because the potential difference across a capacitor rapidly decreases when discharging. Then the 10 ohm bulb was replaced with a 20 ohm bulb, and the charging time of 10 seconds and discharging time of 13.7 seconds was measured. The calculated resistance of the resistors was less than the theoretical values, possibly due to incorrect connection between measurement tools and circuit elements, and other possible sources of error include quality of instruments used, quality of materials used, incorrect instrument calibration, rounding during calculations, and timing error. If you charge the capacitor with no resistor in the circuit, the ideal model would predict the capacitor to charge instantaneously, since the resistance is equal to 0. In real life, this prediction would not occur because every circuit element has a small amount of internal resistance. The experimental time was not measured.